The night sky looks still, but it is alive with motion we cannot feel. Each star drifting overhead is a moving fragment of a greater machinery, and the darkness between them is not empty. What we see is a fragile skin stretched over a structure too vast to comprehend. The paradox begins here. We believe the universe is scattered with objects, yet the deeper we look, the less it behaves like a collection of things, and the more it feels like a single, connected breath. From a quiet hillside, the Milky Way appears as a smear of powdered light, but every grain in that arc is a star, and beyond each star lie billions more in other galaxies. The numbers run away from us. If you try to count them, even language fails. 1 trillion stars, a quadrillion planets, unthinkable distances, and still, none of these numbers touches the limit. Somewhere beyond imagination, clusters of galaxies weave together into webs, and even those webs are only threads in a greater tapestry. What could be larger than everything we already call vast? Imagine a star so immense it could replace our sun and swallow all the inner planets. Stevenson, 218, or Scuti. Names whispered among astronomers. Are red supergiants so large that light itself needs hours to travel from their centers to their surfaces? If such a star sat where our sun now burns, its surface would stretch past Jupiter. The sky from Earth would be nothing but a red horizon. Yet, in the scale of the cosmos, that monstrous sun would still be small. Far beyond it wait black holes millions, even billions, of times the sun's mass. Invisible engines that shape galaxies and silence the birth of new stars. We once thought galaxies were islands, separate, isolated, entire, but gravity links them like beads on invisible strings. The farther our telescopes reach, the clearer the patterns become. Clusters merge into superclusters, superclusters into filaments, and those filaments twist around voids so wide that entire groups of galaxies drift through them like dust across an ocean. When researchers traced these patterns, they found walls of galaxies stretching billions of light years. The Sloan Great Wall, the Hercules Corona Borealis Great Wall, structures so immense that their existence strains the principle that the universe should look roughly the same in every direction. Why does the universe build such colossal shapes? Gravity should have pulled matter together into smaller, tighter knots, while cosmic expansion should have stretched everything apart beyond connection. Yet between those opposing forces lies a balance so delicate that it allows webs, clusters, and voids to coexist. The laws of physics permit it, but they do not easily explain it. Are we observing accidents of random clustering or signs of deeper symmetries written in the first seconds after creation? Simply put, the search for the largest thing in the universe is not about finding a single object. It is a test of how far our senses and theories can reach before they collapse under their own assumptions. What do we mean by size when we speak of space-time itself expanding? What do we measure against when the yardstick stretches as we look? The word large begins to lose its edge. It becomes a question of perspective, of where we stand in the flow of cosmic time. The boundary we can see, the horizon of light that marks the farthest photons able to reach us, forms a sphere roughly 46 billion light-years in radius. But that edge is not a wall in space. It is a limit in time. We are not peering to the outskirts of a place, but to the beginning of a story whose opening chapters are still arriving. Every photograph from the most powerful telescope is really an image of the past, a fossil of light billions of years old. The further we gaze, the younger the universe we behold. Consider how small we are against that clock. Our entire species has existed for less than the blink of a cosmic eye. The photons that strike our detectors tonight left their galaxies long before Earth had oceans. Each new observation is both discovery and memory. We are watching the universe remember itself, one faint glimmer at a time. In everyday language, what we call the edge is simply the part of the universe that has had time to send light our way. Beyond that boundary, there may be more of the same, or something utterly different. The data cannot yet tell us. The silence itself becomes a map of ignorance. It is the largest structure we have, drawn not by what we see, but by what we cannot. And so we climb this invisible ladder of scale. First the stars, then the galaxies, then the walls and filaments that frame all we can perceive. Each rung promises answers and leaves us with deeper puzzles. The largest thing in the universe may not be a thing at all, but the reach of perception itself. The mystery is not how big the cosmos is, but how far consciousness can follow it. If cosmic scales fascinate you, tap like and subscribe to the Quiet Universe channel. Ahead of us lies the first step on this ladder, where burning giants dwarf our sun and hint at forces that rule everything beyond. The search for the largest things begins close to home, among the stars that burn around us. We live beside a modest one, stable and bright, but it is hardly representative of what the cosmos can build. Scattered across the galaxy are suns that defy proportion. They swell until gravity itself seems unsure where to draw the line between surface and sky. These are the red and blue supergiants, the swollen hearts of stellar evolution, and each one is a slow explosion held together by its own weight. Imagine standing where our sun is now and watching the horizon vanish under a crimson glow. A single hypergiant could stretch past the orbit of Jupiter, its outer layers tenuous as smoke, its light dimmed by distance yet fierce enough to boil planets if they drifted too near. The pressure inside such a star is beyond language. Fusion blazes through elements heavier than carbon, a chain reaction at the edge of balance. They are both fragile and unstoppable, living fast, shedding mass like shrapnel from an unseen storm. When they die, they scatter the raw ingredients of worlds. Their existence poses a contradiction. Gravity should crush matter inward, yet these giants expand outward until their own radiation almost overcomes their pull. The physics of that balance is a razor edge, one that determines whether a star ends quietly or rips itself apart. Many of them, nearing the end, breathe out shells of gas that form luminous nebulae, glowing reminders of a core soon to implode. The spectacle is not rare, but we rarely see it, because distance blurs detail. What we call a point of light might be a sun large enough to engulf our entire solar system. Why do stars reach such absurd scales? Part of the answer lies in their birthplaces, the cold clouds of hydrogen where gravity first begins to gather atoms. In regions where the clouds are especially massive, gravity can pull so much matter into a single core that the resulting star becomes unstable from its first moment. For a few million years, a heartbeat in cosmic time, it burns with furious energy. Then it collapses, sending shockwaves that seed the next generation of stars. The universe builds complexity through cycles of death. In plain terms, the larger the star, the shorter its life. A red supergiant might live only a few million years before it explodes. Our sun, small and efficient, will shine for billions. Yet the giants, in their brief fury, forge the heavy elements that make rocky planets and human bodies possible. Without their violent deaths, there would be no iron in blood, no carbon in breath. Size, it seems, buys spectacle but not longevity. At the edge of visibility are monsters larger still, stars whose dimensions are so vast that even naming them feels poetic. Some are so bloated that astronomers argue whether they should be called stars at all or transitional objects teetering on the brink of collapse. Their photospheres are cool, glowing in deep reds, but their interiors churn with violence. Observations reveal vast convection cells, each one larger than our entire orbit. Material drifts upward, cools, and falls again in waves that last centuries. These are suns in slow motion, sleepwalking toward extinction. From Earth, they appear serene. Through a telescope, they shimmer like calm embers. But if you could hover near one, the light would not be steady. It would pulse, swelling and fading with each surge of heat. The very concept of surface becomes meaningless, because there is no solid boundary, only layers of plasma rising and falling. They are not like furnaces, but like storms that never end. If the sun is a candle, these are worlds of fire. Every measurement we make stretches comprehension. Their radii approach thousands of times that of our sun. The space they occupy could swallow hundreds of millions of Earths. When they cast off their outer shells, the expanding gas can form rings and arcs light years wide. Eventually, gravity wins the final argument. The core collapses, releasing an explosion so intense that it outshines entire galaxies for a few days. These are the supernovae, the moment when matter remembers its origin in violence. And from those ruins, the next chapter of scale begins. The collapsed cores become black holes, dense beyond reason, objects where mass and light part ways. They are the sleeping giants of galaxies. Invisible, yet dominant, at the heart of the Milky Way lies one, quiet now but capable of consuming stars. Compared to that hidden weight, even the largest supergiants are fleeting shadows. Think of it like this: every red sun that dies feeds the darkness that will later anchor a galaxy. The largest stars are both architects and sacrifices. They construct the elements of life and surrender their remains to gravity's hunger. Their stories do not end with death, but continue as seeds for structures we will soon encounter. The question that follows is simple but immense. If a single dying star can shape the chemistry of a galaxy, what happens when the galaxy itself grows a black hole at its center? The next step up the ladder takes us to the point where gravity wins completely. A black hole is not a thing so much as a region, a boundary where escape is impossible. No light leaves its surface, because it has no surface at all, only a horizon where space folds in on itself. It sounds like absence, yet black holes are among the most luminous phenomena in the universe. They glow not by their own nature, but by what they consume. Imagine a core of darkness surrounded by a whirlpool of fire, gas, dust, and shattered stars spiral inward, heating until atoms split and radiation floods every wavelength we can detect. These disks of infalling matter, called accretion disks, shine brighter than the combined starlight of entire galaxies. The paradox is immediate. A black hole, defined by its inability to let light escape, becomes the engine of the brightest beacons in the cosmos. At the center of our own Milky Way lies one of these giants, a few million times the mass of the Sun. We know it not by sight but by motion. Nearby stars race around an invisible point, their orbits tight and frantic, like moths circling an unseen flame. By measuring their speed, astronomers can weigh the darkness. The result leaves little doubt: a supermassive black hole sits at our galactic heart, silent most of the time, but capable of violence on unimaginable scales. In other galaxies, these central engines are more active. Some swallow matter so greedily that their disks blast out jets of particles moving almost at the speed of light. We call them quasars, and they are among the earliest and farthest objects ever observed. When their light reaches us, billions of years have already passed. The energy they release is staggering. A single quasar can outshine 1,000 Milky Ways, burning across the void like a lighthouse that never stops. Why would the universe produce such extremes? The relationship between a black hole and its host galaxy is still being uncovered. It seems that the more massive the galaxy's bulge, the heavier the black hole at its core. It is as if both grow together, feeding from the same reservoir of collapsing gas. When the hole becomes too active, it floods its surroundings with radiation and wind, cutting off the supply of fresh material. Star formation halts, and the galaxy begins to fade. Out of destruction comes regulation. The cosmic predator also plays gardener. At its core, this balance between growth and feedback governs the evolution of structure. Galaxies do not simply accumulate stars, they rise and fall through phases of feeding, quenching, and rebirth, all under the watch of their central shadows. The black hole is both engine and governor, a tiny region controlling a vast city of suns. If you could stand safely at a distance and watch a quasar, you would see a disk glowing hotter than any furnace, wrapped in magnetic fields that twist matter into jets. Those jets pierce intergalactic space, stretching for millions of light years. They carve channels through gas clouds, compressing and heating the medium between galaxies. The energy in a single jet could power all human civilization for the lifetime of the universe. Yet from that far away, the galaxy around it would be invisible, drowned in brilliance from its own center. Simply put, a black hole can become so radiant that its host vanishes from view. Telescopes must tune themselves to see around the glare, studying the faint outlines of stars and gas that survive the storm. The discovery of such objects has forced us to rethink what luminous means. It is not only stars that make light. The act of falling, of losing energy to gravity, can light up the cosmos more fiercely than creation itself. For decades, astronomers wondered whether all galaxies hide such beasts. Evidence now suggests they do. Even small galaxies show signs of compact masses at their cores. When fed with gas, they awaken briefly, radiating across X-ray and radio bands. Then they sleep again for eons, leaving only a whisper of their past activity. The Milky Way's black hole is in such a slumber. Occasionally it flickers, releasing faint bursts of energy that remind us what it could still become. In everyday language, think of a black hole as a power plant that uses gravity instead of fuel. The deeper matter falls, the more energy is released. Infall turns into light, pressure, and motion. The system is nearly perfect in efficiency, converting a significant fraction of mass into pure radiation. The result is spectacle born from collapse. These cosmic engines do more than illuminate. They sculpt galaxies. Jets and winds push gas into intergalactic space, seeding distant regions with heavy elements. The same radiation that halts star formation in one place can trigger it elsewhere. Nothing about a black hole is truly isolated. Even its silence echoes across millions of light years. Why it matters is simple. Understanding these dark giants reveals why the universe looks the way it does. Without them, galaxies might have formed endlessly, creating overcrowded skies and no clear structure. With them, order and emptiness alternate, a rhythm of birth and restraint. Every map of large-scale structure bears their influence. Yet mysteries remain. We have measured black holes billions of times the mass of the Sun, existing less than 1 billion years after the Big Bang. How did they grow so fast? Theories propose runaway mergers or exotic seeds, left from the first stars. But direct evidence is scarce. Each new observation pushes the timeline closer to the beginning. Perhaps the earliest universe favored rapid collapse, or perhaps our understanding of gravity itself needs revision. For now, we watch. Instruments like the Event Horizon Telescope, linking radio dishes across Earth, have imaged the shadows of these giants, confirming that the fabric of space behaves as Einstein predicted. The result is haunting. A glowing ring of matter orbiting a void, light bending until it loops upon itself. It is a portrait of energy surrendering to geometry. The more we learn, the more the boundary between light and darkness feels symbolic. The brightest places are born from the darkest centers. When black holes outshine galaxies, they remind us that absence and presence are part of the same design. If the cosmic web of energy and gravity captures your imagination, like and subscribe to the Quiet Universe channel. As the engines of galaxies fall quiet, our view must widen again, outward into the clouds of gas and dark halos that surround them, where the invisible begins to shape what we think of as reality. Beyond the glowing centers of galaxies lies an expanse that challenges both our sight and our certainty. We picture a galaxy as a pinwheel of stars, bright arms curving gracefully in space. But that is only a luminous skeleton. Around and within every spiral stretches a veil of matter we can hardly detect. The deeper we look, the more the edges fade, until we realize the visible part is just the core of something much larger and stranger. Our instruments catch the ghostly outlines first, faint arcs of light that barely rise above the noise of the sky. some galaxies. Like Malin appear as pale disks so extended that they dwarf the Milky Way, yet they shine 100 times dimmer. To see them, telescopes must stare for hours, stacking photons one by one like grains of sand. These ghost disks are real, vast, and quiet, holding their shape where physics says they should have fallen apart. What holds them together? The answer, or at least the clue, comes from motion. Stars in the outskirts of galaxies move too fast. According to Newton's laws, they should drift away into space, but they do not. Their speed implies that gravity is stronger than what visible matter can provide. Something unseen wraps around them, a halo of mass without light. This is where dark matter first revealed itself, not through visibility but through insistence. The galaxies refused to behave, and the equations bent toward a missing ingredient. In plain terms, the visible part of a galaxy is like the flame of a candle, while the dark matter halo is the invisible air that shapes the flame's dance. The stars we see occupy only a fraction of the space governed by gravity. Simulations show that a galaxy's true boundary extends many times beyond its disk, an enormous sphere of influence filled with unseen particles. We do not yet know what those particles are. They do not shine, reflect, or absorb, yet their presence explains the pattern of cosmic structure on every scale we can measure. These halos are not static shells. They merge, stretch, and sway as galaxies collide. When two spirals meet, their luminous disks twist apart, forming tidal streams of stars. But the halos blend smoothly, creating a common envelope. The result is not chaos, but renewal. New galaxies emerge from the debris, each encased again in a dark cocoon. The cycle resembles the growth of living cells dividing and merging, though on scales of millions of light years. Why it matters becomes clear when we follow the trail of light. Without these halos, galaxies could not hold their stars long enough to form complex worlds. The gravitational glue that keeps spiral arms intact also protects solar systems from being flung into the void. The invisible scaffolding of the cosmos is not a poetic phrase. It is the literal architecture that allows luminous matter to persist. At its core, dark matter is an act of humility. It reminds us that most of what exists does not speak our language of light. We know it only by its effect, by the way it bends the path of starlight or accelerates the spin of galaxies. Every map of the universe is, in truth, a shadow of a deeper map we cannot yet draw. Consider the outskirts of a typical galaxy. Out there, the density of stars drops until individual suns drift like lanterns in fog. Yet the rotation curve, the plot of orbital speed versus distance, stays flat. This flatness is one of the most stubborn facts in astronomy. It refuses explanation unless mass continues beyond the visible rim. Every student who studies those curves learns the same uneasy lesson: our understanding of gravity and mass is incomplete. Some researchers propose alternatives, tweaking gravity itself to account for the motion without invoking unseen matter. But such theories falter when tested against larger structures, like galaxy clusters or the cosmic web. The consistency of the missing mass across scales suggests a common cause. Whatever dark matter is, it behaves coherently, linking the smallest halos around dwarf galaxies to the vast filaments that connect clusters. Simply put, galaxies are the luminous frosting on an invisible cake. The majority of their weight lies in darkness. Through gravitational lensing, where massive objects bend background light, astronomers have traced the contours of these halos directly. The patterns confirm what rotation curves imply. Dark matter forms the skeleton of the cosmos. Without it, the universe would be a mist of isolated stars, never gathering into galaxies, never giving rise to the chemistry of life. In human terms, imagine walking through a city at night where only the street lamps are visible. You would see the lights, but not the streets, the buildings, or the air that carries the sounds. The lamps hint at structure, but not substance. That is our view of the universe. Every shining galaxy is a clue, and between them stretches the unseen infrastructure that binds the whole together. The paradox deepens when we realize that the same halos that stabilize galaxies also limit our view of them. Much of a galaxy's gas is trapped in hot, tenuous form, too diffuse to glow in visible light. Only through X-ray telescopes do we glimpse these coronae, vast clouds spanning hundreds of thousands of light years. They mark the transition between galaxies and intergalactic space, a boundary that is more gradient than wall. Matter flows through it slowly, recycling between stars and the medium beyond. The visible disk is just one expression of a much wider ecosystem. Why do these ghostly forms matter to us? Because they tell the story of balance. The universe is not only explosions and brilliance, it is restraint and persistence. Dark matter halos cradle the fragile disks where light can emerge. Their gravity steadies the orbits of stars that might host planets. In a way, everything we call home owes its stability to something we cannot see. Think of it like this: the cosmos is a grand cathedral whose pillars are made of shadow. Light streams through, tracing patterns on the floor. But the real structure is hidden in the dimness. The harmony of form arises from what refuses to shine. As telescopes grow sharper, astronomers are learning to map the darkness by its influence on light from distant galaxies. They find filaments extending from halo to halo, connecting islands of matter into an enormous web. The halos, once thought to be isolated, are now understood as nodes in that web. The story of scale continues outward. The invisible shapes we trace around galaxies merge into a framework that fills the universe. Soon, we must leave the quiet elegance of individual galaxies behind and follow those filaments into the open cosmic sea, where matter gathers not in disks, but in rivers and sheets that stretch across hundreds of millions of light years. From the faint halos and ghostly disks, we now descend back into the luminous heart of cosmic architecture, where galaxies collide, merge, and grow through a kind of cosmic hunger. A galaxy is not a static island of stars, but a restless city, constantly reshaped by gravitational tides. Every large spiral or elliptical we see is the product of countless mergers, each one rewriting its shape and identity. In this slow violence lies the story of scale pushed to its limits. Picture two galaxies drifting toward each other over billions of years. At first, their outer halos meet like clouds blending in the wind. Then, as they draw closer, stars from one begin to feel the pull of the other. Tidal forces stretch them into long tails of light. From afar, these arcs resemble streams frozen in time. Over centuries, the cores spiral together until they fuse, and what remains is no longer a pair but a single, bloated structure. Gravity is not a gentle sculptor. It is a patient devourer. Some of the largest galaxies known, like those that anchor massive clusters, are swollen by this process. They sit at the centers of cosmic congregations, surrounded by smaller companions that drift inward like moths to a flame. With each collision, the central giant absorbs new stars, gas, and dark matter, swelling its halo. Astronomers call these systems CD galaxies, central dominant giants whose envelopes can span over 1,000,000 light-years. From their outskirts, the glow fades imperceptibly into intergalactic space, a gradient between order and void. Simply put, they are cities that never stop annexing their suburbs. Their central regions shine with the combined light of hundreds of merged galaxies. If we could stand within such a system, every direction would show clouds of stars overlapping, a sky with no darkness between constellations. The night would be a sheet of continuous light, soft yet omnipresent. The mechanics of galactic cannibalism are inevitable. Small galaxies lose energy as they orbit larger ones. Friction within their halos and the drag of gravitational tides cause them to spiral inward. When they finally collide, gas clouds compress, triggering bursts of star formation. Then, when the central black holes merge, they can unleash jets that sweep clean the remaining fuel, ending the starburst and leaving behind a calm but massive remnant. Growth and silence alternate like breath. Why does the universe favor this cycle of creation and consumption? Because structure itself seeks equilibrium. Gravity gathers matter into dense regions, and those regions draw in more material. The result is a hierarchy. Small galaxies merge into larger ones, and large ones dominate clusters. The cosmic web is not uniform, but top-heavy, feeding its mass toward the deepest wells. In plain terms, think of a galaxy cluster as a great plain dotted with oases of light. Over time, streams of matter flow toward the largest oasis until it swallows the rest. The same law that pulls an apple to Earth scales up to sculpt the entire cosmic landscape. It is gravity's poetry, written in collisions. Some of the most striking examples of this process lie in galaxy clusters, such as Abell 2029 or Coma, where the central giants are so vast that their halos blend with the intracluster light. Between galaxies, there is no clear boundary, only a sea of wandering stars stripped from their homes. Astronomers call it the intracluster medium, a diffuse glow that bridges one galaxy to the next. Within it drifts hot gas, enriched by supernovae, shining in X-rays but nearly invisible to the eye. This glow is the residue of eons of mergers, the smoke of cosmic industry. When a small galaxy approaches a giant, its stars are torn away in stages. The outer ones become part of the halo. The inner ones spiral inward. The gas, compressed by shock waves, ignites brief chains of star formation before being consumed or blown away. Eventually, what remains is a faint core, stripped of its identity, subsumed by the larger system. Nothing is wasted. Every star finds a new orbit within the expanding empire. Why it matters becomes evident when we look at the extremes. The biggest known galaxies, like IC 1101 or ESO 38376, have grown not just by random collision but by occupying the gravitational centers of superclusters. Their growth traces the geometry of the universe itself. Each merger is a record of motion across billions of years. To study them is to read a history book written in starlight. At their core, these colossal galaxies challenge our sense of proportion. Their diameters reach millions of light years, containing trillions of stars. Even their central black holes are among the largest ever detected, weighing billions of solar masses. Yet despite their enormity, they radiate a strange stillness. After the frenzy of growth, they settle into ellipsoidal forms, smooth and featureless, glowing softly with the combined age of countless suns. The contradiction is haunting. The most massive galaxies are also the most sterile. Their gas is gone. Their star formation ended long ago. They shine with the tired light of ancient stars, slowly fading as fuel runs out. The violence that built them also ensured their quiet demise. In them, the universe shows its tendency toward both expansion and exhaustion. Astronomers now use deep imaging and spectroscopy to detect the faint traces of their past feasts. Streams of stars, like tidal fossils, encircle the giants in ghostly arcs. Each arc marks a devoured companion. Computer simulations reproduce these patterns, revealing that a single massive galaxy may have swallowed dozens, even hundreds, of smaller ones. The sky around them is not empty, but filled with debris too thin to see directly. Think of it like this. A colossal galaxy is a monument built from other galaxies' ruins. Its smooth shape hides the chaos of its birth. Every glowing point within it was once a part of another world, another spiral with its own planets and histories. The universe, in its patient indifference, recycles everything. The pattern continues upward. Groups of galaxies merge into clusters, clusters into superclusters, each scale feeding the next. The hierarchy of gravity extends without pause. What begins as a local collision between two galaxies becomes, over billions of years, a web of structures reaching hundreds of millions of light years. These immense systems remind us that even permanence is temporary. The galaxies we see tonight are snapshots in a moving story. Given enough time, the Milky Way and Andromeda will merge too, forming a new elliptical, perhaps named Milkomeda by future astronomers. The night sky then will not have a band of stars, but a soft glowing oval that fills the heavens. Our descendants, if any remain, will look up and see the next stage of the cycle. At its most poetic, galactic cannibalism is the cosmos teaching efficiency. Nothing is lost. Energy becomes light, matter becomes structure, and memory becomes pattern. To witness these colossal galaxies is to glimpse how creation and destruction are the same act seen from different angles. When the giants finish their meals and silence settles, we are left to wonder what structures lie beyond even these. What cosmic gatherings surpass the scale of single galaxies? The answer lies in the filaments and bridges that link one cluster to another, forming the skeleton of the universe itself. From the scale of single galaxies, we now step outward into the architecture that binds them all together. What looked like isolated islands of light are, in truth, connected by strands stretching across the observable universe. When astronomers began to map the positions of galaxies in 3 dimensions, the pattern that emerged was not random. It looked like a vast web, an intricate network of filaments and knots surrounding immense voids. The discovery changed how we see everything. Galaxies are not scattered but organized by gravity into one of the most complex structures ever found. The first clues came from redshift surveys, which record the distance of thousands of galaxies. On the maps, points of light lined up in delicate threads, meeting at clusters where the density was highest. Between them lay immense regions almost empty of galaxies. These gaps, the cosmic voids, give the universe its honeycomb appearance. From above, if one could ever stand there, the cosmic web would look like veins of light glowing against a background of endless night. Each filament is composed of galaxies, dark matter, and gas stretched thin by cosmic expansion. Gravity gathered matter after the Big Bang, pulling it into sheets and threads as the universe cooled. Over billions of years, those filaments thickened, while the regions between them drained of material. What we call the cosmic web is the frozen trace of that evolution, a memory of how gravity sculpted chaos into form. Simply put, the universe is not evenly filled. It is a sponge of matter and emptiness. The filaments serve as highways, guiding galaxies and gas into clusters. The densest intersections become the sites of superclusters, vast congregations of galaxies bound together across hundreds of millions of light-years. These intersections are the cities of the cosmic web, and the filaments are the roads between them. At its core, the web is both delicate and immense. The filaments are thin, only a few megaparsecs wide, but they stretch across distances that defy analogy. Within them flows the intergalactic medium, a tenuous plasma of hydrogen and helium. This gas, invisible to our eyes, holds much of the ordinary matter in the universe. Without it, galaxies would starve, unable to form new stars. The web is not only a structure, but a circulatory system. Think of it like this from far away. A cosmic filament would resemble a glowing river winding through a dark plain, where 2 rivers meet. Currents merge into whirlpools, and those whirlpools are clusters of galaxies. Every glowing spiral, every giant elliptical, has journeyed along one of these invisible rivers, carried by gravity and time toward denser shores. The largest filaments form what we call walls, immense sheets of galaxies enclosing the cosmic voids. The Sloan Great Wall, the CFA2 Great Wall, and the Hercules Corona Borealis Great Wall are among the most astonishing. Some stretch for billions of light-years, so long that they challenge the assumption that, on large enough scales, the universe should look uniform. Are these walls statistical flukes, or hints that our map of cosmic evolution is incomplete? The debate continues, but their presence is undeniable. Why it matters is profound. The cosmic web represents the transition from simplicity to structure, from a nearly uniform early universe. Gravity amplified small irregularities into this grand network. The ripples in the cosmic microwave background, those minute temperature variations, became the seeds of the filaments and walls we see today. The web is the bridge between the birth of matter and the landscapes of galaxies. At human scale, this discovery parallels our own maps of connection. Cities, roads, rivers, power lines, all follow branching networks that echo the same geometry. The universe repeats its logic across scales, from neuron to nebula. Our brains are wired in filaments of information just as the cosmos is wired in filaments of matter. We are, in a sense, built from the same design. But the web is not static. Matter continues to flow along its threads. Simulations show galaxies streaming toward nodes like leaves carried by currents. Over time, clusters merge, voids expand, and the pattern evolves, though the basic framework remains. Dark matter provides the scaffolding, while gas and stars illuminate it. The visible cosmos is just the glowing edge of a deeper shadow. In everyday language, what we call empty space is anything but empty. Between galaxies, thin strands of gas and dark matter stretch across unimaginable distances. They are faint, almost transparent, but they bind the universe together. If those threads vanished, galaxies would drift apart, and cosmic history would stop. The web is the invisible hand maintaining the rhythm of cosmic structure. The beauty of the web lies not only in its size, but in its subtlety. Each filament is shaped by forces that act over billions of years. When light from distant quasars passes through these filaments, it carries fingerprints of hydrogen absorption known as the Lyman alpha forest. These spectral lines are the whispers of the web, allowing us to trace structures we cannot see directly. In this way, light from the farthest objects serves as a backlight, revealing the filaments in silhouette. Why it matters to us is more than scientific. The web redefines our place in the cosmos. Our galaxy is a small spark within the Laniakea supercluster, a flow zone where gravity guides thousands of galaxies toward a common center. Beyond that center, other superclusters stream toward even larger attractors. The picture is humbling. We are not in a single cluster or a single neighborhood, but part of a vast, moving sea. As we map these motions, we begin to see the universe not as static space, but as a dynamic flow. Gravity sculpts the pattern, and cosmic expansion stretches it, an eternal balance between attraction and release. When viewed in computer simulations, the web pulses like a living organism, a slow heartbeat of matter through time. The paradox is that we see this immense structure only through its faintest traces. Most of it is dark matter, unseen, and the rest is gas too thin to emit light. We live inside a masterpiece drawn in invisible ink. The patterns of galaxies across the night sky are just the visible strokes on a canvas of shadow. Think of the cosmic web as the blueprint of the universe, a design printed across billions of light years, connecting every galaxy, every star, and every atom of us. The next step beyond these filaments takes us to their boundaries, where the web meets the largest structures of all, the walls that seem to test the very limits of cosmic order. As we follow those walls outward, we begin to wonder if the pattern itself ever ends, or if it continues beyond the edge of what light can reach. Every time we believe the universe has shown its final form, it presents a scale that should not be possible. Beyond the threads of the cosmic web lie constructions so vast they strain the limits of cosmological theory. In a universe governed by the same physical laws everywhere, we expect large patterns to average out. Yet when we map the sky deeply enough, we find walls and filaments whose dimensions defy that assumption. They are too big, too coherent, and too connected to fit comfortably within the models that have guided us for decades. When the Sloan Digital Sky Survey first revealed the Sloan Great Wall, it stretched across 1 billion light-years of space. Its discovery in the early 2000s shocked cosmologists. Statistical models predicted that such large structures should be exceedingly rare, perhaps non-existent. Instead, this wall appeared almost casual, one among many. Later surveys uncovered even more colossal arrangements, like the huge large quasar group and the Hercules Corona Borealis Great Wall, spanning several billion light-years. At those scales, the meaning of structure begins to blur. How can gravity maintain coherence across such distances when the expansion of the universe should pull everything apart? To put it plainly, These walls are not built from galaxies in neat rows. They are webs within webs, dense regions where filaments interlock and clusters gather. The Great Wall is less a wall in the architectural sense than a continent of matter. Within it, galaxies are grains of sand. It is a landscape that bends the very principle of cosmic uniformity. The cosmological principle, a cornerstone of modern astronomy, asserts that on sufficiently large scales the universe looks the same in every direction. This assumption supports our equations for expansion, the behavior of dark energy, and the interpretation of the cosmic microwave background. But what if it is only approximately true? What if structures larger than theory allows are common enough to tilt that balance? Astronomers remain cautious. Statistical analysis suggests that some of these massive features may arise from chance alignments. Quasars, for example, are so bright that even small clusters can seem like continuous walls when plotted in low resolution. Yet the more data we collect, the more such anomalies appear. Each new survey seems to uncover another impossible structure lurking just beyond the previous horizon. If they are illusions, the universe is remarkably consistent in its deception. In everyday language, the universe should be smoother than it looks. The cosmic web was supposed to fade into randomness beyond a certain scale, around a few 100 million light-years. Instead, patterns persist for billions. It is as though we zoomed out of a painting expecting blur but found new detail instead. Why this matters is not just statistical. If structures this vast truly exist, they challenge the assumption that matter has had time to arrange itself under gravity alone. The age of the universe sets a limit on how far gravity can communicate. To build a wall several billion light-years long, regions separated by more distance than light could travel since the Big Bang would need to act in concert. That should be impossible, yet the data hint otherwise. One idea is that such structures are fossils from the earliest fluctuations in density, imprinted before cosmic inflation ended. Inflation stretched space exponentially, freezing quantum ripples into macroscopic patterns. Perhaps some regions inherited stronger seeds, amplified over eons into the giants we observe. If so, the Great Walls are echoes of the universe's birth pangs, not violations of its rules. Another possibility is that we are underestimating the complexity of dark matter. Its distribution might encourage clustering on scales larger than predicted. Dark matter does not interact electromagnetically, but it shapes the gravitational potential in which galaxies form. Small differences in density could cascade upward, linking distant filaments into megastructures. Simulations attempt to reproduce this behavior, yet none so far match the observed walls precisely. Reality still outpaces our code. Think of it like this. The cosmos is a vast fabric, and these gigantic structures are wrinkles that never flattened. The cosmic expansion was supposed to iron them out, but they remain silent evidence that the universe carries memory in its folds. Even stranger are the alignments found in the cosmic microwave background. Patterns in polarization and temperature appear to point in similar directions as some of the large quasar groups. The connection may be coincidence, or it may hint at an unseen influence guiding the distribution of matter across the largest scales. Scientists call this alignment the axis of evil, a name both dramatic and uneasy, for it implies that the universe has a preferred direction. According to our best theories, it should not. These observations remind us that science advances through discomfort. The things that should not exist are often the clues that reshape understanding. When Edwin Hubble first measured the expansion of the universe, it defied common sense. When dark energy was discovered, it overturned cosmology again. Now the Great Walls test our confidence in cosmic homogeneity. Each contradiction forces us closer to truth. Why it matters runs deeper than the numbers. These structures define the maximum reach of human mapping. We have traced the cosmic web as far as our telescopes can see, and still the pattern continues, repeating in silence beyond our data. If we could step outside our observable bubble, would we find even greater walls? Or would the pattern dissolve into randomness? The answer defines the boundary between science and speculation. The largest structures also invite an existential reflection. If galaxies are atoms in a larger organism, then we are moments inside a process still unfolding. The universe may be growing in layers, and we are seeing only one of them. Perhaps the impossible structures are early scaffolds for something grander still. The scale is so immense that no human lifetime, or even the lifetime of stars, can witness their evolution. They exist in slow motion, moving imperceptibly while we flicker through centuries. In plain terms, we are studying footprints of giants whose strides span the age of the universe. To measure them is to confront our own smallness, not just in space but in time. Yet the search continues, because each discovery teaches us that the limits we imagine are rarely final. Some astronomers argue that the very phrase "should not exist" is misleading. The universe is under no obligation to fit our expectations. Theories are only temporary maps drawn from limited experience. The cosmos remains the territory, vast and unmoved. When data contradict prediction, the proper response is not disbelief, but curiosity. Think of the Great Walls as invitations rather than anomalies. They whisper that reality is richer than the rules we have written. To face them is to admit that understanding is an evolving horizon. These walls are not barriers, but mirrors, showing us the boundary between what we know and what we can imagine. As we continue to chart these immense realms, our journey moves naturally toward the spaces between them, the immense voids that balance the cosmic design. There, in the silence between walls, lies another mystery waiting to unfold. Every generation of observers has faced the same horizon, a limit to how far the universe will allow us to see. Yet each time we approach that boundary, a new instrument pushes it back, uncovering structures that were invisible the year before. The history of astronomy is the history of vision itself, a slow conquest of distance by glass, metal, and imagination. In this race to see more, we are not merely gathering data, we are reconstructing time. When the first telescopes were raised to the sky in the 17th century, they multiplied the number of visible stars by thousands. Later, the great refractors and reflectors revealed nebulae, tiny smudges that would turn out to be galaxies. The 20th century brought radio dishes and space telescopes, machines that collected light our eyes could never perceive. Each advancement widened the known universe, yet each also made its finitude more apparent. No matter how powerful our tools become, light still travels at a fixed speed, and the universe has a finite age. We are trapped inside a sphere defined by time itself. This sphere is the observable universe, a bubble roughly 93 billion light-years across. Its edge is not a wall in space, but the limit of what has had time to reach us since the Big Bang. Beyond it, the universe may continue endlessly, but its light will never arrive. The most distant galaxies we can observe today are snapshots of youth, shining as they were when the cosmos was only a few 100 million years old. To look outward is to look backward. Every telescope is a time machine. At its core, astronomy is an act of listening to ancient light. The James Webb Space Telescope, stationed far from Earth's shadow, has captured faint glows from galaxies that formed soon after the first atoms joined. Some of these appear surprisingly mature, larger and more structured than theory predicted for that era. Once again, the universe refuses to align neatly with expectation. Maybe our understanding of galaxy formation is incomplete, or maybe the fabric of time expands in ways we still do not grasp. Either way, each image extends the edge of what can be known. Think of it like this. Our instruments are boats sailing on an ocean of darkness. The farther we travel, the fainter the shoreline becomes, until we can no longer tell whether the sea continues forever or folds back on itself. The horizon is not fixed. It grows with technology, but it also retreats as the universe expands. Every photon that arrives to our detectors represents a victory over distance and decay. The race to see more is not limited to visible light. Radio telescopes map hydrogen across billions of light-years, tracing filaments of the cosmic web. X-ray observatories reveal the hot gas that fills galaxy clusters. glowing from collisions and mergers. Gravitational wave detectors now add an entirely new sense, hearing the ripples of space-time itself. Together, these instruments weave a multi-sensory map of the cosmos. What we once perceived as silent and static now hums with signals across every frequency. Simply put, telescopes are extensions of human perception. Each one shifts the boundary between ignorance and understanding. When we build them, we are building versions of ourselves that can see farther. The lenses and mirrors are not eyes but promises, declarations that curiosity will not rest. In their reflections lies the oldest light known. Yet even with these marvels, there is a fundamental limit we cannot cross. The cosmic microwave background marks the oldest light in existence, a faint afterglow from about 380,000 years after the Big Bang. Before that epoch, the universe was opaque, filled with plasma that scattered photons endlessly. No telescope, no matter how powerful, can see beyond that curtain using ordinary light. To glimpse earlier moments, we must rely on neutrinos, gravitational waves, or pure inference. The boundary of vision is woven into the physics of existence. Why it matters is not only technological, but philosophical. The horizon defines what science can verify. Beyond it lies speculation, perhaps infinite reality, perhaps nothing. We live inside a cosmic bubble of knowledge, expanding yet forever bounded. Our measurements tell us that as the universe accelerates in its expansion, more galaxies will drift beyond reach. In the distant future, observers in our galaxy may see only darkness, the rest of the cosmos lost beyond the speed of light. The universe will still exist, but it will no longer be visible. In everyday language, we are racing a vanishing act. The more we discover, the more the universe pulls away. Every year, a few thousand galaxies slip quietly beyond the horizon, their light stretched into invisibility by expansion. The edge of the observable universe is not a frontier we can cross. It is one we are losing. And still, we build new eyes. Ground-based observatories like the Vera Rubin telescope will soon map the sky in motion, catching changes over days instead of centuries. Space missions will measure the subtle distortions of distant galaxies caused by dark matter. We are learning to see by proxy, using gravity itself as a lens. Every distortion, every flicker, is a clue. This relentless mapping has an emotional weight. To measure the horizon is to face the end of sight. We are drawing the boundaries of our own knowable world. Yet the act itself carries hope. Each discovery is a refusal to accept blindness. The light from distant galaxies may fade, but its echo will live in our records. At its core, science is not about the conquest of mystery, but about living within it. We push the boundary not to escape the unknown, but to understand its shape. Telescopes, detectors, and simulations are our way of touching infinity without crossing it. They remind us that seeing is a kind of dialogue between curiosity and cosmos. Think of the horizon not as a wall but as a mirror, one that reflects both the universe and our persistence. The farther we reach, the clearer our own limits become. And those limits give the journey meaning. The darkness beyond the edge is not a void. It is the next question forming. Why it matters to us is deeply human. To chart the universe is to affirm that our brief existence can still comprehend eternity. When we map the faintest galaxies, we are mapping ourselves into the cosmic story. Every photograph, every spectrum, every signal is a small rebellion against the silence of time. Soon, the race will enter its final stretch, not to see farther, but to understand what distance itself means. Beyond the outermost galaxies lies the horizon of causality, where space and time blend. There we will confront the largest boundary of all the particle horizon, the true measure of the universe's reach, and the edge of what can ever be known. At the limit of distance, our instruments falter. The final images arrive stretched into whispers, photons diluted by time, their wavelengths elongated into silence. We have followed light as far as it can go, and it leads not to a border in space, but to a boundary in understanding. The universe ends not where matter stops, but where comprehension reaches its edge. The largest thing we have found is the sphere of our own perception, the horizon that wraps around every direction. To study it is to look back at the beginning, to glimpse the faint afterglow of creation that still hums through the background of night. When we speak of horizons, we usually imagine distant lines, places where the sea meets the sky. But in the cosmic sense, the horizon is not a line we can approach. It is a mirror made of time. Every photon that reaches us carries the memory of an earlier universe, younger and denser than the one we inhabit now. The further we look, the less we see of space, and the more we see of history. What we call far away is simply long ago. In this reversal, perspective becomes humility. We are surrounded by the past, enclosed by it like an echo trapped inside a vast chamber. Simply put, the universe does not stretch outward from us. It stretches backward through time. To look up at the night sky is to read a chronology written in light, where the faintest galaxies mark the earliest chapters. Somewhere, beyond the limits of what light can cross, the story continues unseen. The shape of that unseen realm is unknowable, but its presence is undeniable. It presses against the edges of our equations like an ocean beyond the shore. The philosophical weight of this realization is immense. Every map, every measurement, every photograph is framed by what we cannot see. Our understanding is a small island of knowledge surrounded by an infinite sea of silence. Yet within that island, the precision of our models and the reach of our tools are astonishing. The same species that once mistook stars for candles in the sky has now measured the curvature of the universe to within a fraction of a percent. The contrast between what we know and what we cannot know defines our era. In everyday language, we have learned to measure the immeasurable. We can describe the temperature of the cosmic background to the nearest millionth of a degree. We can count galaxies across billions of years of distance, but we cannot tell what lies beyond the horizon, nor whether there is an outside at all. The observable universe is our bubble of existence, and its surface is both the beginning and the end of observation. At its core, the question of the largest thing transforms into a question about ourselves. If the boundary of the observable universe is the largest structure we can define, then we are not outside it looking in. We are inside it, suspended in the middle of our own horizon. Every direction we look is both inward and backward, the edge of reality. Then, is not a wall, but a memory. Why this matters is deeper than science. It forces us to consider the difference between existence and awareness. The cosmos may extend infinitely beyond what we can detect, but for us, the universe ends where knowledge ends. Each new discovery expands that border a little farther, yet it remains a moving frontier, chasing light that will never quite arrive. We live within the expanding aftermath of a single moment of creation, witnesses to an explosion that still unfolds in silence. Think of it like this. The universe is a film still developing, and we are watching from within the frame. The edges of the picture are unfinished, still waiting for light to reach them. What we call the known universe is the portion of the image that has already come into focus. The rest, the part we cannot see, is not emptiness. It is potential. Some imagine other universes beyond ours, born from the same cosmic inflation that gave us this one. Others propose that space is finite but unbounded, curving back on itself like the surface of a sphere. Both ideas share a strange kinship. They imply that our horizon is not the end of being, only the end of reach. Whether infinite or closed, the cosmos refuses to present a final answer. The further we progress, the more we are reminded that knowing is an act of translation, not possession. The ancient paradox returns to observe the universe is to change our place within it. Each new telescope, each new measurement, pulls us farther from the illusion of centrality. We are not at the center of creation, nor at its edge. We are a midpoint in a story that may have no boundaries. The very act of looking defines the field we observe. Awareness becomes part of the structure itself. When we trace the cosmic web, we are tracing the distribution of matter, but we are also tracing the outline of curiosity, the way intelligence maps its environment. Somewhere in the midst of that web, on a small planet orbiting a modest star, consciousness has arisen to reflect on the whole. This reflection is not incidental. It is the universe folding back upon itself in thought. The observer is not apart from the cosmos, but an expression of its capacity to know. Why it matters to us is both fragile and profound. In an existence where the largest structures dwarf imagination, meaning must come from scale of thought, not scale of matter. The quiet of space is not emptiness, but invitation. When we map galaxies, we are answering that invitation, joining a dialogue written in light. Each observation, no matter how small, is a conversation between the finite and the infinite. At its heart, this pursuit is not about conquering mystery, but about learning to live beside it. To accept that there are horizons we cannot cross is not to admit defeat, but to recognize wonder. The edge of the observable universe is not the end of truth. It is the beginning of awe. Every unanswered question is a doorway, and every measurement is the footprint of a species that refuses to stop asking. The final image is quiet. A lone telescope stands beneath the black sky, its mirror open to the faintest light. Above it stretches a sphere of time, filled with ancient radiation, galaxies, and voids, all drifting outward into eternity. The silence is not cold but patient. The sky does not reply. Yet every glimmer of starlight is a message already sent. And so the echo returns, soft but unbroken. If the largest thing in the universe is the horizon of our own perception, then to see is to create meaning within the limits of sight. The open question remains when we finally understand the shape of everything we can see. Will we be ready to face what lies beyond?